Hi, I'm John Swoboda. I work at MIT Haystack Observatory. This presentation is on data processing quality analysis using the simulator for incoherent scatter radar for the Millstone Hill incoherent scatter radar. I've done this work with colleagues Bill Rideout, Phil Erickson, and Frank Lynn, where I work with at Haystack. So one of the main jobs we have at Haystack is working on the Millstone Hill atmospheric radar. This radar essentially sends out electromagnetic waves up into the atmosphere. Those waves reflect back, and those specific waves have a power spectral density associated with them, which you can derive through first principles physics models if you have requisite plasma parameters such as electron density, ion temperature, electron temperature, and ion velocity. Now, since you can make those these spectra that I have in the diagram below using those plasma parameters, you also can back out those plasma parameters if you're giving a specific spectra. When we're generally doing our incoherent scatter radar processing, we are fitting for that center line, the ion line that you see in the diagram, which is very narrow in spectrum and also much more powerful, much higher SNR than the other lines. And what I have above the diagram is basically the incoherent scatter radar spectra from the Millstone Hill incoherent scatter radar, just in case where we have, or we're putting in each range, one of those spectra. So you can kind of think of that diagram as just one single row, and you can see how the spectra varies with range from the antenna. Now, one of the main things we do with this system is we, again, create measurements of plasma parameters in the ionosphere. Those plasma parameter measurements are used in various studies. For example, from Hickey et al. 2014, where Destin Hickey is looking at the midnight temperature maximum. He's using data from the Millstone Hill incoherent scatter radar to see if at these latitudes you could actually detect this. And the data he's using, in this case, ion temperature, he's using the plasma parameter value, the measurement, and then also the error bar associated with it. So you can get an idea of uncertainty between the two, between the measurement parameter you're given and the uncertainty. So those are the two main things we deliver with this system. Now, this is just a case where we're doing a short-term experiment. It's over a single day, but you want to make sure you're able to repeat it, in case you do different experiments at different days or different times. You want to make sure you're comparing everything properly. This becomes even more important when you go to longer-term studies. These are cases that from Zhang and Holt, two different papers. The first first image on the left is showing the variability of the ionosphere over a 30-day run at Millstone Hill. And you can see that there's a lot of variability even day to day. And also in the case of climatology, it becomes even more important with climatology studies. So in the case on the right-hand side, where there's a lot of variability, and you're trying to get an overall averaging of the plasma parameters over a very long period of time. And this involves very large data sets, so you want to make sure your processing is stable over those times and predictable as well. And so you understand if you change something in your processing, that how will it affect longer-term measurements. Now, this is where SimISR comes in. Now, this is a software package I developed while I was in graduate school that essentially creates voltage level data for ISR. And the way it does that is it takes a white Gaussian noise plant for each range A, essentially, or each. We then take that noise plant, we filter the data. The filter is based off of the power spectra you would get from an incoherent scatter in the ionosphere. So that's the shaping filter. In this case, a filter for ACF. And that filter is created using the plasma parameters. And then it's shaped with a window. In this case, the pulse shape for the radar system, because you need to keep that in mind as well. And then you put it in a big delay line to represent range, and then add them all up. And then you filter it and add noise as if it was a real radar receiver. So you have this raw data, and you can use it for various things. In the past, I've used it to look at inversion algorithms and see how well they are, test different algorithms, see if they create any extra artifacts that could be problematic. But in this case, we're using it just to test processing chains. Now, we wanted to move our processing chain itself from a grid, I'm calling it grid structure, which is essentially we have a dedicated machine that processes the radar data, to a cloud infrastructure where we have a virtual machine in a cloud computing environment, and we can just easily repeat processing over and over again in a cloud architecture, because this is rather complicated software, so you don't want to have to reinstall this software processing chain all the time working. Now, as we were doing this, it was realized by Bill Rideout we have to change our numerical libraries, because we were using an older Python numerical library called numeric, and we were moving that to NumPy, which is the general numeric language now, or numeric package for Python. We wanted to know if this would create any subtle changes in the processing, because these subtle changes could be amplified during the fitting. If you're trying to fit those power spectra and get real plasma parameters out of it, there could be big changes because of just the way this inverse problem is set up. Now, to do this, we created a stream of digital RF data from SimISR, which is a file format for raw RF data that was developed at Haystack, and is used by a lot of our by our radar itself and also other sensors as well that we have. Now, for SimISR, essentially what we did was we took just some plasma parameters from an arbitrary day, and we derived those plasma parameters. I used the MSIS and IRI models through PyGlo, and just created a set of plasma parameters that varied with time, that varied with altitude, and we wanted to make sure that they would, and we used both a long pulse coding scheme for one set, so we looked at both long pulse data and alternating code data. For the case of alternating code, we kind of stopped looking at things over about 300 kilometers, because we generally aren't using alternating code data beyond 300 kilometers. And we took this same thing and we ran it through both our grid processing chains and the cloud processing chain. And if you look at just the plasma parameters, it looks on a large scale pretty much the same. We're not seeing any large differences. You really have to zoom in and be very careful about the way you're doing this. And in each case, you're looking at data from on the top, which is the cloud processing, and then versus the grid mode. And again, the grid mode was the original processing chain we were using. So in both cases, there isn't that much difference. And as you can see from this, especially in higher, you're just looking from a high level. Now, when we go to error comparisons, the way I'm doing these error comparisons, we want to see what happens as, say, the noise level gets higher comparatively to the signal. And we want to see how that changes the error bars. And this allows us, again, another way to compare, the grid processing versus the cloud processing. And in this case, the grid mode is on top and the cloud mode is on the bottom for each of these. And the structures here, what you're seeing here is on the x-axis, which is noise over signal, or 1 over SNR. And then on the y-axis is the error bar for a specific parameter. And essentially we call these S-curves, and these should move sort of as an S. As you get higher, as you get a higher noise level, you end up with a higher and higher error bar from the fitting. So, and then you kind of peak out as you get to more and more noise, it kind of flattens out. And if you're looking at these, you really can't see much difference between the different processing chains. They seem to operate very much in the same way. You may see some changes when you get to very, very high noise levels, but for the most part, they track each other pretty well. Now we get to raw differences, and also just subtracting the two parameters, the output from the two different chains. So first one on the left-hand side is just the raw parameter differences. And the problem is you can't really see too much because a lot of times the raw parameter differences are so small you can't tell anything that's useful from this. So instead, what I did was I took the error bar from each of these and actually normalized the different parameters by the error bar instead, and try to get an idea of when is, say, the difference larger than 10% of an error bar, or and just tried to get those lined up there. And for the most part, we're really, really below, say, for example, a fifth of an error bar or quarter of an error bar in most cases. And, I then went and took this data a little bit further and looked at the percentage of outliers, which I said, okay, if you have a difference that's greater than an error bar, let's look at all those differences. Let's look at those specific outliers. And for the most part, those outliers, all of them at SNRs, less than 1, which generally is low quality data. It really just noise here. And then of those percentages, looking for outliers for each of those parameters that have greater than SNR greater than 1, they're all less than 1%, about 0.5% or less. Meaning that for the most part, the explanation for anything that's outside these error bars could be there's just noise in the system. And also looking at the rest of these, any of these outliers that are above SNR of 1, they were all very low altitude and had very narrow spectra, so that can easily cause problems with the fitting for these parameters. To make sure that we weren't fooling ourselves by looking at a small data set, we expanded this and looked at different examples of, say, for example, equinox or solstice examples, which I took using either IRI model. I used an IRI model for that, same as we did before. And also we looked at a storm example, which we took from raw Millstone Hill measurements. And again, you're seeing a similar plot from before, but just with a lot more data on the order of 1 million samples per case, and was following the same general trend. So, we thought for the most part this was settled, and we thought that this change in processing isn't going to affect our measurements in any appreciable way. In the end, we decided to just move ahead and modernize our processing pipeline. But now we have a tool where with SimISR that can output data in a format that the radar processing can ingest. And so what we can do now is we can use this to take in data and do A/B testing of our different processing chains if we may want to adjust our processing in different ways as well. And I'll be updating SimISR more to actually make this in a more configurable manner, so you can use this for different radar systems, or at least you put in parameter values of a different radar system. And we're actually interested in using this method to inject data into the receivers, where we're going to take the SimISR data and just run from a radio, from a software-defined radio, and just inject that data directly into the other radio that may be receiving the data. And this way we can do that. We're going to A/B test also receivers as well. And we have to definitely automate this testing though, and be able to, this way we can do more A/B testing on processing chains as we change things. Okay, thank you.